Hello and welcome to yet another lecture on control system, paper code PCEE 503. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is time-domain analysis of a standard second-order closed-loop system. Lesson objective: after end of this topic, student will able to understand the concept of time domain analysis of a standard second order closed loop system. So let us take a RLC series circuit. This is a RLC series circuit, where the V suffix IT stand for the input to that particular circuit, and the V0T stand for the output from that particular circuit. And the current that is circulating through the circuit is IT. So if I take the Laplace transformation, the VIT became VIS, IT became IS, V0T became V0S, and C became 1 by CS, and L became LS. So the IS is the voltage at that point is VIS, and voltage at that point is V0S. So VIS minus V0S by R plus SL, and the V0S is the voltage across the capacitor, that is IS into 1 by CS. So this is the entire block diagram, where input is VI, yes, it is multiplying with the gain called 1 by RS, which is getting that this is the input VIS and this is the output V0S. So it is this, in this portion the total output is VI minus V0S. So it is multiplied with 1 by R plus SL, it will give IS, this one. And when IS is multiplying with 1 by CS or SC, it will give the V0S. The output. So now if I concentrate on the open loop transfer function. So the open loop transfer function GS equal to 1 by SC R plus SL. So it is clear that the highest power of the AC in denominator is 2. So the order of an RLC circuit, series circuit, is the 2. Order of the RLC series circuit is 2. Now we are dealing a closed loop transfer function. From the previous size, it is clear that the open loop transfer function is 1 by SC to R plus SC. So the feedback that is given to the particular system having a value of Hs equal to 1. The value of feedback is 1. So the closed loop transfer function, we all know that is given by the equation is Gs by 1 plus Gs Hs. Just putting the values of Gs. And we are getting our closed loop transfer function. Here the Hs equal to 1 that I have already told is the feedback part. So the closed loop transfer function became 1 by S square LC plus S RC plus 1. So if I take the LC part common, it will give that 1 by LC equal to S square plus R by L into S plus 1 by LC. So this is the RS is the input, and the transfer function is given that 1 by LC by S square plus R by L into S plus 1 by LC equal to CS. So we can compare the equation with this one, omega n square by S square plus 2 zeta omega ns plus 1 by LC. So this equation we can compare. This equation can easily be compared with that particular equation. So it is clear after comparing that omega n square equal to 1 by LC. So omega n equal to 1 by root over LC, where omega n stands for undamped natural frequency of the system. And if I compare 2 zeta omega n equal to R by L, so zeta became R by 2 root over R into LC. This is called the zeta is called the damping ratio. So the total transfer function can be written in that way: C by R equal to omega n square by S square plus 2 zeta omega n S plus omega n square. But the characteristics polynomial is generally this part, the denominator part of that equation, the standard transfer function equation. So it is given that Qs equal to S square plus 2 zeta omega n S plus omega n square. So Qs equal to 0 will give the characteristics equation, means root of that particular equation. That is nothing but the closed loop poles. The root of the characteristics equation means after getting the characteristics polynomial, putting characteristics polynomial equal to 0, we are getting the values of s, which are generally known as roots of the characteristics equation. That is the closed loop. So the roots, that is s1 and s2, are given by the equation minus zeta omega n plus minus omega n into root over of zeta square minus 1. But s1 and s2 are the roots of this equation called Euler's the characteristics equation. So by the comparing the standard equation, by comparing the these two equations, the series RLC circuit transfer function with that standard transfer function equation, we get omega L equal to 1 by root over LC, and the 2 zeta omega n equal to R by L. From that particular equation, we are getting the value of zeta equal to R by 2 root over LC after putting the value of omega n, where omega n is known as undamped natural frequency, and the zeta is generally known as the damping ratio. So the equation, the standard equation of a transfer function of a second order system, where this equation, that is s square plus 2 zeta omega n s plus omega n square, it is known as characteristics polynomial. Putting this equation equal to 0 is called the characteristics equation, where the roots of the equations are given by the equation. That is, the roots of the equation, say s1 and s2, are given by the equation minus zeta omega n plus minus omega n root over of zeta square minus 1, where s1 and s2 are the closed loop poles. So depending upon the value of the zeta, we obtain the pole location from the particular system. So if the zeta value is lie between 0 to 1, if the zeta value is lie between 0 to 1, the pole location S1 and S2 are the complex conjugate. The pole locations are seen in this figure. This is the pole location. These are the pole location, that is the complex conjugate. These are the pole locations. And the nature of the time response is called the underdamped response, and it is look like this one. The nature of the time response is called the underdamped response. So when the value of the damping ratio lies between 0 to 1, the S1 and S2 are getting from that particular equation, that one, S1 and S2 are getting the complex conjugate, which is the pole location, and the nature of the response is called the underdamped response, and it is given by that graph. The nature of that particular graph is given by that particular equation. This is called the underdamped response. This is called the underdamped response. So when now the case 2 is given, that when zeta equal to 1. So when zeta equal to 1, this portion is omitted. So the value of S1 and S2 is the minus omega n from that equation. The value of S1 and S2 are minus omega n. So it is clear that the value of this one and S2 is the minus omega n. This is called the pole location when zeta equal to 1. So the nature of the system is the critically damped system. So the nature of the system is when zeta equal to 1, the nature of the system is called the critically damped system and it is called the faster response. This is the nature of the system called the critically damped system and it is also known as the faster response. Now, if zeta greater than 1, the case 3 is given that if zeta greater than 1, the S1 and S2 are the real and unequal. It is clear in the whole location that the S1 and S2 are the real part and they are the unequal. And it is called the zeta 1 means the it is called the overdamped response. And this is the response is known as the overdamped response and it is sluggish in nature. So for zeta equal to 1, we are getting the critically damped response. That is the response of the system. For zeta greater than 1, we are getting a response called the overdamped response and corresponding pole locations are real and unequal. Now case 4 is that when zeta equal to 0, the value of S1 and S2 is the plus minus j omega n means there is no real part. This is the j omega n, this is the minus j omega n, this is called the imaginary axis. This is the pole location. Plus minus j omega n. And the response is means zeta equal to 0 means there is the damping ratio is 0 means there is no damping in the system. Zeta equal to 0 means there is no damping in the system, so the response is known as the undamped response. So there is no damping in the system is there. This is called the undamped response. This is when the zeta equal to 0, this is known as the undamped response. So depending upon the different values of zeta, that is called the damping ratio, we are finding the different response of the system. So just capture those, just memorize those things that for zeta equal to when the zeta value lies between 0 to 1, the response is called the underdamped response, and this is the pole location. For zeta equal to 1, this is the pole location, and the response is known as critically damped system, and this is the fastest response. And if the zeta greater than 1, and this is called the pole location of the system, and the response is known as overdamped response, which is sluggish in nature. Now, when zeta equal to 1, the response and S2 are called the underdamped response because that zeta equal to 0 means there is no damping in the system. So this is the pole locations, there is no damping is there and response is called the underdamped response. So let us, this is a general equation of a second order system, general transfer function of a second order system where Rs is the input and Cs is the output, and this is the transfer function omega n square by s square plus 2 zeta omega n s plus omega n square. This is the standard form of a transfer function of the second order system. Now, if I provided the step input in this system, that is Rt equal to Ut equal to 1, so in Laplace domain it is called the Rs is called the 1 by s. So the Cs is 1 by s into, so we all know the transfer function is Cs by Rs, this one. So Cs is 1 by s into this one. So we can write the equation in this way that by the partial fraction method, this is the way to write the entire system by the partial fraction method that is seen in this form. That it is 1 by s minus s plus zeta omega n by s plus zeta omega n whole square plus omega d square minus zeta omega n by s plus omega s plus omega zeta omega n whole square plus omega d square. So this is how this is formed, that equal to 1 by s minus s zeta omega n by s plus zeta omega n square plus omega d square minus zeta omega n by omega d into omega d. Means we are taking the omega d part here, multiplying with omega d. So we are getting this zeta omega n by omega d into omega d by s plus zeta omega n square plus omega d square. So s square plus 2 zeta omega n s plus omega n square, this part. This part can be written as a square plus zeta omega n whole square plus omega n square into 1 minus zeta square. So this is known as the damped natural frequency omega t square. So omega t square equal to omega n square into 1 minus zeta square. This is called the damped natural frequency. So from that particular equation, omega n by omega t equal to 1 by root over 1 minus zeta square. So from that particular equation, it is find that omega n by omega t equal to 1 by root over 1 minus zeta square. So I am putting those values there. I am putting those values here in this equation, but the previous equation here. I am putting those values, just putting those values of omega t here. So I am what I have getting that I am getting a response at time domain or time response, that is CT. It is given we are getting a CS in this way by taking the inverse Laplace. We are getting CT equal to 1 minus e to the power minus zeta omega nt cos omega dt plus zeta y e to the power 1 minus zeta square e to the power minus zeta omega nt sin omega dt. So response at time domain or time response. So this is the time response when I am taking zeta equal to cos theta, cos phi. So in this way, if I take zeta equal to cos phi, it will be treated as 1 minus e to the power minus zeta omega nt by root over 1 minus zeta square into root over 1 minus zeta square cos omega dt plus zeta into sin omega dt. So now I am taking the zeta equal to cos phi. So the equation becomes uh, 1. This equation became 1 minus e to the power minus zeta omega nt by root over 1 minus zeta square into sin theta cos omega dt plus sin omega dt plus theta. So the CP became 1 minus e to the power minus zeta omega nt by root over 1 minus zeta square sin of omega dt plus theta. This is called the underdamped response when zeta belongs to 0 to 1. This is generally known as the underdamped response when zeta is belong to 0 to 1. So if I take the specification of time responses, this is the graph for the specification of the time responses. So one is called the delay time TD, one is called the rise time TR, one is called the peak time TP, one is called the settling time TS, and another is called the maximum peak overshoot MP. So the definition of the delay time is the time taken for the response to reach the 50% of the final value. So the final value of that response is this one. Time taken to reach the 50% of that final value, this is called the TD. This time, this is the time axis and this is the uh, output axis, and this is the RT equal to UT, that is the unit step input is given. So time response is the final value, and time taken to reach the 50% of the final value, that is this one, say. So this one is known as the TD, the delay time. Then the next is the rise time. Time taken by a response to reach the first final value. So the first final value is this one. This is the graph that is approaching to its final value 1. So time taken for the graph to reach the first final value, that is this one. This is called the TR or the rise time. This one is called the, when a perpendicular from here, this is called the TR or rise time. Peak time, the third one, is the time taken for the response to reach the first overshoot. This is called the first overshoot, first undershoot, second overshoot, second undershoot, and in this way. So time taken for the graph to reach the first overshoot. This is the first overshoot, first undershoot, second overshoot, second undershoot. So time taken for the graph to reach the first overshoot is called the TP, that is the peak time, T suffix P. This one. Another is the settling time. It is given that the time taken for the response to reach 2 to 5% of the tolerance band, that is called the TS. So time taken for the graph to reach that 2 to 5%. This is the 2 to 5% of the tolerance band that we can tolerate to reach the final value. This is total time is known as the T suffix S. This is called the settling time. Another is called the maximum peak overshoot, that is M suffix 3 P. That is it is the difference between the maximum peak value and the reference input value. So this is the maximum peak value, and this is the reference input RT, and this is the maximum peak value. It is the time difference between the maximum peak value and the reference input is known as in suffix p or maximum peak overshoot. Now we are doing the calculation part. Now how we can able to approach to the calculation of the rise time. So rise time means the time that we have. If we just go through the definition of rise time, that the time taken for the response to is the first final value. So when the response reached to its first final value, means when t equal to tr, the entire value became, the output became 1. So this part became 0. If this part became 0, so the entire output become 1. So this part became 0 means the sign part became 0. So sine omega t plus phi equal to 0. So t now replaced by the tr when there is the output ct when t equal to tr equal to 1, because at rise time t equal to tr, the graph reach the first. It's clear that time taken for the response to reach the first final value, that is the final value 1, that is called the tr, first final value 1. So there it so the output must be 1 when this part is 0. This part means the sine part is 0. So from that omega dt tr plus phi equal to 0. So tr became minus phi by omega d. This is called the rise time. So if I take cos phi equal to zeta, so sin phi equal to 1 minus zeta square. So tan phi equal to root over tan phi equal to sin theta by cos theta equal to root over 1 minus zeta square by zeta. So zeta equal to 1 minus root over zeta square by zeta. So phi equal to tan inverse root over 1 minus zeta square by zeta. So tr became minus 1 by omega t. Just putting those values there, phi tan inverse root over 1 minus zeta square by zeta. So this is the calculation of rise time. So peak time calculation, TP. Peak time means, so if I go to the definition, peak time means time taken for the response to reach the first overshoot. Means the first order derivative of at t equal to Tp, the output, first order derivative, that is with respect to 2 ddt of Ct will be the 0. So if I put those values and do the first order derivative of Ct, we are getting that particular equation, that is zeta omega n sine omega t sine of omega d plus t plus phi equal to omega d cos of omega d plus t plus phi. So by sine by cos this part, it is called tan omega d plus phi equal to omega d by zeta omega n. Putting the values of omega d by omega n, it will be 2 to the power 1 minus zeta square by zeta. So this part is nothing but the tan phi. So sin omega dt plus phi equal to tan phi. So when t equal to Tp, so tan phi can be replaced by tan omega dt plus phi equal to tan n phi plus theta. So at t equal to Tp, so omega d Tp equal to n phi. So Tp equal to n phi by omega t. By the values of the n are 1, 2, 3, 4. So n1 it is stands for first overshoot, n2 stands for first undershoot, that I have already told. N3 stands for second overshoot, and N4 stands for second undershoot. So in this way, that value of the peak time Tp is finding. So Tp equal to n pi by omega t. This is called the peak time. So another is the maximum peak overshoot. So for the calculation of the maximum peak overshoot, it is MP, that is output Ct at t equal to Tp, means at t equal to Tp, the value of output minus RT. Because if I go through the maximum peak overshoot, that is the output, that is the difference between this reference maximum output is given, that is the difference between the maximum peak value and the reference input value. So at t equal to Tp means that t equal to Tp, that is the peak time. T equal to Tp at peak time, what is the value of that graph? Minus 1. So output at t equal to Tp minus RT, that is 1. Just putting those values, we are finding this equation. Here n equal to 1 because it is the first overshoot. So n equal to 1, just putting those n values, we get omega dt equal to n phi. So omega dt Tp equal to n pi, so it is not pi. So Tp equal to pi by omega t. So sin theta equal to 1 minus zeta square. Sine, because Sine pi minus theta equal to minus sine theta. So sine theta equal to 1 minus zeta square. Just putting those values, mp that we are finding is that e to the power minus zeta omega n tp, e to the power minus zeta omega n tp. So it is e to the power minus zeta omega n pi by omega t. So mp value is e to the power minus zeta pi by e to the power 1 minus zeta square. It is the value of the maximum peak overshoot, mp. So the value of the settling time is, value of the delay time td is 1 plus 0.7 zeta by omega n equal to td, and value of the settling time for 2% tolerance band, it is ts equal to 4 by zeta omega n, and for 5% tolerance band, it is ts equal to 3 by zeta omega n. So if zeta greater than 1, it is the overdamped response and can be given as ct equal to 1 minus a to the power a to the power minus at minus b to the power minus at. If zeta equal to 0, it is called the undamped, and the ct equal to 1 minus cos omega nt. If zeta equal to 1, the output is this one. So the critically damped or the fastest response, ct equal to 1 minus e to the power minus omega nt into e to the power omega nt plus 1. So we have learned about different type of systems. We have learned that about the different types of system. So and the time specification, that is the peak time, rise time values. So let us take a problem. It is given that for what value of the k and a, for what value of that k and the a, the damping ratio is 0.7 and the undamped natural frequency is 4 rad per second. So this is the closed loop transfer function omega n square plus 1 plus 2 theta omega n s plus omega n square. So it is nothing but the gs equal to 1 plus gs hs, where gs equal to given by k by k, this one open loop transfer function. Open loop transfer function is given by k by s into s plus 2, and where hs is given by 1 plus as. Just putting those values, we are getting that equation k by s square plus k plus 2s plus ak. So just comparing those two equations, we are getting k plus 2 equal to 2 zeta omega n and ak equal to omega n square. So from that particular value, omega n is 4 is given and zeta equal to 0.4. So ak equal to 16, that is the 4 square, it is already given, omega n equal to 4. So k plus 2 equal to 2 zeta omega n, just putting those values, k value is 3.6 and a value is ak equal to 16. So a equal to 16 by k, 16 by 3.6, that is 4.4. So value of k is 3.6 and value of a is 4.44. By comparing those two equations, we can able to solve that particular problem. So another problem is that the open loop transfer function of a unity feedback system is given by gs equal to 25 by s into s plus 5. Find tp, tr, ts and percentage of mp overshoot. So the characteristic equation that is given by 1 plus gs hs. So gs equal to this one, 25 by s into s plus 5, and hs equal to 1 because it is given that the transfer function of an unity feedback system. So h is equal to 1. So 1 plus gs h is equal to 0. From that we can find the equation that s square plus 5s plus 25 equal to 0. We are comparing with the general second order system represent, that is s square plus 2 zeta omega n s plus omega n square equal to 0. So from comparing those two, omega n square equal to 25, so omega n equal to 5 rad per second, and 2 zeta omega n equal to 5, so zeta equal to 0.5. So we have to calculate the TP, that is pi by omega t, pi by omega n over 1 minus zeta square. Just putting those values, so the omega d value is 5 into over 1 minus 0.5 whole square, that is 4.33. Just putting those values, we are finding that TP equal to 0.725 second. Now TR, that is the rise time, that is minus omega minus 5 by omega t. So phi is pi minus omega t by omega t in radian, where phi is in radian. So phi is tan inverse root over 1 minus zeta square by zeta. So tan inverse minus 5 equal to tan pi minus 5. For minus 5, tan inverse minus 5 equal to tan pi minus 5. So phi equal to tan inverse root over 1 minus 0.5 square by 0.5. So phi is 1.0475. So from that we can easily find the phi. Just putting the value tr equal to pi, that is 3.14 minus 5, 1.04 square by 4.33, that is 0.43 seconds. Now settling time for 2% tolerance line, it is 4 by zeta omega n, 4 by 0.5 into 5, that is 1.67. And for 5% tolerance line, it is 3 by zeta omega n, 3 by 0.5 into 5, that is 1.27. Second, and we are calculating the percentage of overshoot, that is percentage of NP equal to e power minus zeta pi by e power 1 minus zeta square into 100%. Just putting those values, we are getting 16.3%. So in this way, the problem is solved. So thank you. Today we have learned about the closed loop response of a second order system. This is the time driven analysis of a second order system along with the different response specification. That is the peak time, delay time, rise time, maximum peak overshoot, settling time, conception. So that is called the time driven analysis of a standard second order closed loop system. Thank you.